Yeah, the last day of finals are, I think, the 26th.
My final is on Wednesday. Just what we did last time.
For which class?
My abstract algebra class with Arthur Berrigar.
Oh, yeah. Okay. Good luck.
Oh yeah. The sad thing is that algebra 4 at UNLV is basically just algebra 2 but harder. But like I got 100% on the last test, so I think I'll be fine. And I've taken all 4 algebra classes now, so uh
Algebra
maybe
4 as an abstract algebra, right?
yeah.
Okay. So yeah, how does the naming scheme work?
Um well, something like algebra 1 or 2 in high school should be renamed to topics in like mathematical grammar, honestly. It's not real algebra. But abstract algebra kind of refers to the study of things like permutation groups or fields, which will be important for our discussion today. I mean, not that important. So, but like, let's see, was this the one we defined vector spaces in? But abstract algebra just encompasses a wider range of things. It's you can kind of think of like algebra as generalizing how objects act in each other with different operations. If you think of it that way, then that's what abstract algebra is about. Was it
I see. Okay.
you have the group of permutations?
Is that your
Also,
only final?
yep, that's my only class even.
Wait, really?
Taking all that's the last math class at UNLV that's interesting to me.
So wait, is that like the end of undergraduate?
Yeah, I have one elective to take. Basically, the last elective that I have to take it has been a humanities elective, and I really just hate online discussions. And but for the last year, the only humanities available has been online discussions.
That genuinely sucks. Yeah, online humanities discussions don't that doesn't sound very good.
The only upside is it allowed me to take graduate combinatorics too, which is literally the best experience in my entire life. But yeah, otherwise it does suck. But I've taken all the math classes at UNLV that they have offered that sound interesting to me. So
So what are you doing for grad work?
um,
Isn't that like the
I'm probably going to travel abroad, not doing grad school before I do grad school. I would because the thing is that I can make money, and my time at UNLV has demonstrated that I learned better under my own direction. Um, I I have a project that essay I sent last time. I would like to finish that before I leave, and I would show that to Dr. Berrigar or someone, um, and use that to secure some letters of recommendation. I probably could get one from Dr. Berrigar and from Dr. Robinette because I got A's in their graduate classes. But give someone a real reason to write a letter for me. Anyway, so last time we basically defined what a vector space was. I think that was 2 times ago. Defined the vector space axioms. Let me see if I can find that one. I guess I'll just start a new page. The horrible problem is that I guess OneNote has decided to lag if the files get even halfway big. So I'll just call this wedges 511-11. That'll make more sense. I'm going to get rid of these. So let's just recall what the vector space axioms were. And so first you're going to start with a field of scalars. So what does this mean? These are number sets like the rational numbers, the real numbers, the complex numbers, the integers mod a prime number, or exotic things. But the unifying feature that these all have is division by a not equal to 0 is well defined. So this is basically just a number system where we can divide. So then you consider lists of those scalars. I'm going to just call them n lists, and we're going to assume they're all of size n. And these n lists satisfy these 9 properties. So V0 is that, let's call this our vector space Vn. Okay, so we want to build this vector space. So V0 is that Vn is closed under 2 operations, which we're going to call plus and dot, but these are vector addition and scalar multiplication. And so last time I kind of wrote out what these were, but this time I'm just going to say plus is associative. And then we also have that plus has an identity, the 0 vector. So what that means is we have this equation, any vector plus the 0 vector is equal to that vector. And then V3 was that plus commutes. I think I might have switched the order from last time, but it's not really that important. We just need these properties. We don't really need them in a particular order. V4 says that our 0 vector, our 0 in our field. So we could have a field, any one of these things. I'm just going to call it F. As long as it's one of those, it doesn't matter. So we take the 0 in our field, and if we multiply that, scalar multiply any vector, we're going to get the 0 vector. So I just want to be real specific about the difference between our 0 element of our field and the 0 vector of our vector space. But later we say that, you know, these things are all the same object. Might as well call this like 0 bivector, something you think of that as a 0 area. So then the 5th property was that if we took the multiplicative identity of our field and we multiplied it by any vector, that would give us our vector. 2 more properties and 3 more properties. So V6, we have A, B, V is equal to, in parentheses, A, B, V. And we could just say that this isn't quite, I guess we can say just scalar multiplication is associative. And so the final 2 properties give us a distributive law, and it justifies the name multiplication. So there are a bunch of reasons why you might want to call an operation multiplication, but if it distributes over some other thing that you're calling addition, then it's a pretty good time to call it a multiplication, right? So we have this distributive law, but we also have this distributive law. All right, and so these properties are pretty important, but you'll see them a lot in your first linear algebra class. And with these 4 properties, we almost have a group under addition. We're not sure of, this doesn't say anything about the existence of inverses for our vectors, but that's actually a theorem. So we got 4 simple like coherence theorems that really make this algebraic object that we set up to act like arithmetic. So if we do a vector plus the -1 element in our field and we scalar multiply that by our vector, we're going to get the 0 vector. So this was the first thing that we proved. And this is what let us complete our group. This was the missing property. And then we also have that anything times the zero vector is equal to the zero vector. And then if we have that any scalar times a vector is equal to the zero vector, then either A is equal to the zero in our field, or our vector is equal to the zero vector. And then the fourth thing we proved is that -1 of a vector times a vector is unique. Okay. So, all right, we have all these properties, all these theorems. We have some sort of picture, but this is a really abstract definition. Let's give some examples. And these three examples are basically extremely pertinent to us. So we have the first example is coordinate-free arrows in space. And this is one of the main ways that we think about geometry in like a competition setting, where we don't want to necessarily coordinate bash a problem, but we still want to be able to understand how displacements work. So then this is the first example. The second example is actually subspace representatives under addition. And if we're going to look at mostly this today, this is actually where we left off somewhat last time. Last time we left off, we were about to prove that any two subspace representatives are scalar multiples of each other. So we're going to prove that today. After some examples, we're actually going to do a bunch of examples first. I want to prove all the determinant lemmas today, and then talk about how the Pascal matrices relate to Taylor series. I think we can get it all done today because we kind of have to develop the same solution for 3 of the individual problems. So that's nice. Because the third example is actually polynomials of degree n. And basically, we're going to see that the Pascal matrix L that we had from our P equals LU is equal to a Taylor change of basis, which gives us Taylor series. So we will get to see the problem of how do we find a Taylor series from a linear algebra point of view. So that's what I would like to end with today. And one more comment on this is you can sort of think of as a series as a infinite dimensional polynomial, but the details of making that work is the subject of real analysis. So I'm just sort of pointing at a door for you. And a and you can have something like a Taylor series be an infinite dimensional matrix, or like the process of converting a series into a Taylor series is evaluating an infinite dimensional matrix product. So cool stuff. This is just a comment on what you could do with what we would develop though. So we already did coordinate-free arrows in space, and we had some big questions about that because we were investigating how to identify subspaces of vector spaces, things that are subsets of our vector space that are themselves a vector space. So we came up with this tool in order to identify things. So, well, here, let me look at the next page of my notes. So we're basically asking is how to identify bases of subspaces and when to sets span the same space. Okay, and in order to do that, we invented a wedge product. And this thing, we called it wedge. Unfortunately, it's unfortunate that this symbol is used for a lot of other things in mathematics too. But this is what we're calling it. So this was an anti-symmetric product. I should say vector product, actually. Vector product. So what this means is that it's associative and distributive. It better be if we're calling it a product. So let's look at an example to recall what the details were. So I'm going to give you 3 sets of vectors. And I want you to tell me what the spans of these vectors are. Okay, that's our first set. Or even, is this linearly independent? That's a good question to ask. Should I remind you guys of what the definition of linear independence is? Or can someone remind me?
It's if one of the vectors can be derived with the other two, then it's linearly dependent.
Yeah.
Or with some
so elaborate on what you mean by derived.
Using some algebraic process, you can make one into the other.
Yes, the algebraic process of taking linear combinations of them, right?
Yeah.
But yeah, so one of these sets of vectors is not linearly independent. So let's try to identify that. At a glance, it's not obvious, especially because I can't see anything in 4D. I've never seen anything in 4D, so it's hard to picture it. I don't even know if my brain is built for it. It would probably melt my eyes out to see something in 4D. So the computational answer
is the first one, right?
It is the first one, is row reduction. And when you solve a linear system of equations, or there's tricks you can do. It's kind of obvious because I picked small combinations here. Computational answer. But the best strategy, the ones that computers do, the ones that you'll make money if you improve, you'll be fabulously wealthy if you improve it by 1%. That's row reduction. But we can actually see this still has a lot to do with wedge. I'm not really going to comment on that because you'll do so much row reduction in college. It'll probably make your eyes melt. So the first one is actually linearly dependent. And what that means is we can picture these 3 arrows in whatever 4D space that they're in is actually lying in the same plane. So my fingers are all in the same plane. And so if we remove any one of them, the other 2 still define the same plane. And we would like to understand that particular plane. So now I'm going to rewrite these and let's evaluate them. So number 1, I'm going to write it as the vector E1. This is called E1 because it just has a 1 in the first component and zeros everywhere else. And then the next vector is E1 minus 2, E2 plus 2, E3 plus E4. And then the third vector is 3E1 minus 2E2 plus 2E3 minus E4. So what the wedge product says is we can wedge these together. So if you do this wedge, and it's associative, so I'm just going to do them 2 at a time. Okay. Before I do this, I'll give you a chance to try to evaluate this one. But also on a test you guys took recently, there was a particular geometry problem, and I came up with a solution while I was driving. So I want to see if anyone else was able to solve this one.
Which test?
The one you took at Dr. Wu's house on Saturday?
Oh, I shouldn't take that.
Well, it's a good geometry problem, and I think we could definitely solve it. So,
Oh, it's this one. Yeah.
were you able to solve it?
I didn't do this one. I stuck more to number 3.
Okay. So let's call this area A1, this area A2. Oh, these are angle bisectors. So A1 plus A2 equals 100. What is the total area of the parallelogram? This is a great problem. So I'll give you guys all class period to try to find the solution to this one. And we can compare answers at the end. So now I'm going to perform the wedge product algorithm on this thing. So E1 wedge E1, we proved that that was 0. So then we have minus 2 E1 wedge E2, and then we have plus 2 E1 wedge E3, plus E1 wedge E4, and that's it. Okay. Now we have to wedge this with the other thing. So I'll scroll down a little bit. Minus 2 E1 wedge E2 plus 2 E1 wedge E3 plus E1 wedge E4 wedge 3 E1 minus 2 E2 plus 2 E3 minus E4. All right, so this might look like it's going to be annoying, and it's going to be kind of annoying, but a lot of things are going to help us out here, because instead of having to do 4 to the power 4 multiplications, we actually can make way less, since this wedge this is 0. We don't have to worry about that. This wedge this is 0. We don't have to worry about that. So the first thing that we're going to have to worry about is minus 4 E1 wedge E2 wedge E3. And then we're going to have a plus 2 E1 wedge E2 wedge E4. And then we're going to have, from the second term in the first vector, we're going to have minus 4 E1 wedge E3 wedge E2, and then a minus 2 E1 wedge E3 wedge E4. And let's make this parenthesis a little bit bigger. We don't need a parenthesis because then the product will be done. We'll just have linear combinations. Then finally, from the last term, we're going to have a minus 2 E1 wedge E4 wedge E2 plus 2 E1 wedge E4 wedge E3. All right, so it turns out we can actually combine like terms in this. So if you look, we have a 1, 2, 3 here and a 1, 3, 2 here. So can someone remind me of the definition of antisymmetry? Antisymmetry means that if we interchange two products, then it reverses the sign of the term. And the way that we were thinking about that is we would take the parallelogram formed by A and B, and we would give it an orientation counterclockwise or clockwise. So this is A and B, this is A wedge B. And if we reverse the orientation, we would say that was our additive inverse of this area piece. So this thing is B wedge A right here. A wedge B, B wedge A. Let me make this minus sign a little more obvious right here. So that was our definition of antisymmetry. And so if we apply it to these two terms, we can actually rewrite this as 4E1 wedge E2 wedge E3. And this cancels out with this. So then let's look at this thing, E1 wedge E2 wedge E4. We have this thing right here. It has a sign of -2, but if we rewrite this as 2E1 wedge E2 wedge E4, then these cancel out. And then if we look at this one, E1 wedge E3 wedge E4, then
they cancel out.
you don't think it's loud.
You're changing one into a positive while the other's also
Oh,
positive.
that's true. That's true. Did I make a sign error? I totally could have. That should be our litmus test. So let's just make sure I did all the signs correctly. E2, E1, E3, E1, E4. Okay. Copied it down correctly.
And then down here, they're also correct.
All right, let's see if I can remember the linear combination that I did to rewrite this one. So if we call this V1, V2, then I'm pretty sure I did 3 is it linearly independent? And did I just do my arithmetic wrong on the linear combination? Where did my notes go? They're over here. Did I copy it down incorrectly? It looks like I did copy it down. No. That's just V1 plus V2. That's what it should be. Yeah, so this sign is wrong. But then I wrote it correctly here. Then I wrote it incorrectly here. Okay, did I write it incorrectly up here? No, I didn't. So that turned into a minus sign when it should have stayed a plus. So then that makes this term with a 4 be a plus and this term with a 4 be a minus right here. Oh, sorry, -2. Oh, now it's not writing. There we go, -2. So now we can cross it out because now this changes and this changes. And this flips to a 2, E1. Good catch, good catch. E4, minus sign, cancels, cancels. So we get the 0 trivector, I guess. What are these things? What is the computation that we just performed? Like, what we had is, okay, 3 arrows in a 4D space, but when we tried to find their 3-dimensional volume, or yeah, their 3-dimensional volume in the 4D space, it turned out to be 0. It didn't really actually matter that the space outside was 4D in this case because they were linear combinations of each other. If this is V1 here, V2, we don't have to imagine it as a Cartesian basis, but we could. Is basically the picture we have, V1 plus V2. So I want to do these products. So Matt, how about you do number 2? Ashraf, you do number 3. And I'll try to do these as well, and then we can compare our answers when we're finished.
You said I took number 3, right?
Yeah, okay, you do number 3, Ashraf, you do number 2? I'll do both. So we have E1 minus E3.
I'm attempting to prove that when wedged together, they don't produce zero, right?
Yeah, we want to know specifically what they produce. If they produce zero, that means it's linearly dependent. But if it doesn't produce something that's zero, then it's producing a representative of our subspace. This is something that tells us the specific plane that we're dealing with, the specific like orientation in space that the three vectors take up in 4D space. All right. Can I scroll down a little? Sure. Do you want to see this computation again? Should I write down the let me write down Matt's real quick. So that was okay. If this is a little tedious to you, and you're asking yourself the very natural question of how do you speed this up, the answer is row reduction. If you improve row reduction at all, you'll probably make tons and tons of money. You'll never have to worry about your prospects. You can get a job anywhere. But we're taking the conceptual view. So we're going to have a little bit more computational costs so that we can maintain a top level conceptual view. I made one of the classic blunders. Matt, for yours, if you factor the 4 out of the first vector and then do the wedge product, your numbers will be a lot smaller. And you can avoid it's pretty easy either way, but if you can factor something out of your vectors, it's good to do that.
Right, because it's distributive. I should have seen that.
Well, don't feel bad. I should have seen it too.
I'm assuming, I'm not assuming, but I should also probably factor a 2 out of my third.
Yep. Scroll up a little. Yep. Is there a part in particular you want to see? Should I zoom out?
And I'm just now realizing I wrote my second vector down wrong. Okay.
All right, I'm gonna actually start. I'm gonna do Ashrith first because his is gonna be a lot nicer, and then after we factor the stuff out of yours, we should have a good time. So let's do that. All right, where did I just set my pen? Right here. Okay, so for Ashrith, what we were doing is E1 minus E3, wedge E2 plus E3, wedge. The final one was E1 minus 2 E2 minus E2, sorry. E2 minus E3. All right, so if we do the first one, then we get E1 wedge E2 plus E1 wedge E3, and then minus E3 wedge E2. And then we're wedging that with this vector, E1 minus E2 minus E3. Did I write that down correct? Let's make sure I wrote that down correct. I didn't even write that down correct. Okay. That should be E2, E3, E4. Well, it's still pretty easy to do. We get minus E1 wedge E2 wedge E3, and then minus E1 wedge E2 wedge E4, and then plus E1 wedge E3 wedge E2, minus E1 wedge E2 wedge E4, and then final terms were just a plus E3 wedge E2 wedge E4. All right, I guess we don't need parentheses because we're finishing the product. But let's see about combining like terms. If we flip the sign on this, we can combine it with this for a minus 2 E1 wedge E3, sorry, wedge E2 wedge E3. All right, and then these two things also add up to a minus 2. Right, so minus 2 E1 wedge E2 wedge E4. And then I'm going to take another minus sign out, E2 wedge E3 wedge E4. So might as well pull a minus sign out of this to E1 wedge E2 wedge E3 plus 2 E1 wedge E2 wedge E4. And then we have a plus E2 wedge E3 wedge E4. So that's pretty nice for us. All right, now let's look at the second one. And I'm just going to triple check to make sure I wrote this one down correctly. Okay. All right. So I'm going to write this down in the ugly form, and then we'll see how to make our lives easier. Plus 4E3 plus 2E2 or E4. All right, so what we want to do is we want to factor out all the scalars that we can, all the greatest common divisor of the coefficients. So we can pull a 4 times a 2 times, and then E1 plus 2, oh, now starting to lag, 2E2 minus E3 minus E4 wedge 5E2 plus E3 minus 2E4 wedge minus E1 minus E2 plus 2E3 plus E4. All right. So we have 8 times, this is going to be 5E1 wedge E2, and then a E1 wedge E3, and then a minus 2 E1 wedge E4, and then a plus 2 E2 wedge E3, and then a minus 2 E2 wedge E4 with a minus 5 E3 wedge E2 and a plus 2 E3 wedge E4. So that was all of our 3 terms. Let's see. 1, 2, 3, then 2. Good. Okay, 2. And then we should have 2 more. Minus 5 E4 wedge E2 minus E4 wedge E3. And then wedge our other piece. Okay, let's just try to do some cancellation while we're here so that we have to distribute less. So there's only, this one's unique, okay. 1 and 3, 1 and 3, 1 and 3. This one's unique, all right. Here, let's just write them down here preemptively. All right, 1 and 4s, that's also unique. All right, 2s and 3s. So we have this and this. So that's going to be a minus, sorry, I'm going to put a plus 7. E2 wedge E3. And then that takes care of that. So 2 and 4, that's going to be a plus 3 E2 wedge E4. And then finally, that's going to be another plus 3 E3 wedge E4. And then wedge with this little thing, minus E1 minus E2 plus 2 E3 plus E4. All right, so as we do this, nothing we can factor out of there. So this is going to be 8 times 10 E1 wedge E2 wedge E3 plus 5 E1, wedge E2, wedge E4. And then a minus E1, wedge E2, wedge. Oh, that is the wrong order. Wedge E3, wedge E2. E3, wedge E2. Plus E1, wedge E3, wedge E4. And then we have a plus 2 E1, wedge E4, wedge E2. Minus a 4E1, wedge E4, wedge E3. And then a minus 7 E2, wedge E3, wedge E1. And a plus 7 E2, wedge E3, wedge E4. All right, almost there. 4 more. So then minus 3 E2, wedge E4, wedge E1. Plus 6 E2, wedge E4, 4, wedge E3. And then a minus 3 E3, wedge E4, wedge E1. And then a minus 3 E3, wedge E4, wedge E2. All right. So now we just have to simplify, see what we get. So out of this, I know that there's also this thing, which is just a sign away. So let's put 8 times. Let's see if we can find any others. Here's another one. And then that's it. So we have 10 plus 1. And then it's going to take 2 swaps to get the E1 to the front. So that's going to be minus 7. So we get 4 E1, wedge E2, wedge E3. Actually, there's only going to be 4 terms. I don't need that many. 4 E1, wedge E2, wedge E3. And how am I doing on time? All right, good, good. We haven't used an hour yet. Great. I wanted to have at least one good computational example. So then let's try to find E2, E1, E2, E4. Here's another one. What? Let me circle that correctly. And this is the third one, I believe. Okay, so 5 minus 2 minus 3 is 0. Let me just check what we did up here. Well, that's a huge problem. Great, we get to see where the mistakes crept in. So if we flip this, that becomes a minus sign. So we're getting plus 0 of those. And then we have this, this, and this. Okay. So that's 1 plus 4. Excuse me, minus 3 is 2. So plus 2, E1, wedge E3, wedge E4. And then finally, did this go away? I don't know why that went away. So we have 7 minus 6 minus 3 is minus 2 E2 wedge E3 wedge E4. All right, so that almost looks like asterisk, but it's incorrect. It's definitely incorrect. So I meant for these two things to represent the same subspace. So let's see if I can recover the linear combinations that I made of them. So this one right here, if this is V1, V2, V3, then this one was 4V1 plus 4V2 plus 4V3, I think. Not going to erase. All right. V2 plus 4V1 or V3, which is responsible for our ability to factor the 4 out of it. And then this one was 3V2 plus, or is that minus 2V3, I think? No, plus 2V3. Yep. And then this one was minus 2V1 minus 2V2 and then for V3 we had minus 2V3. That would make sense because we could factor the 2 out of everything. Let me just triple check this. Because if these are all correct, then that just means we made a computation mistake somewhere farther down, which is easier to check. Okay, the first one's correct. Second one's correct. All right, it looks correct. So that just means I did this computation incorrectly. So let's at least make sure that we have the right vectors. So that's going to be 4E1, 4, 8, minus 4, minus 4, 5, 1, minus 2, minus 2, minus 2, 4, and 2. So we factored out the 8. So we got E1 plus 2E2 minus E3 minus E4, 5E2 plus E3 minus 2E4. Then minus 1 minus E1 minus E2 plus 2E3 plus E4. All right, so let's start tracing it out. So this got us this, this got us this got us this. This is this. This right here. Is this wrong? That looks wrong. All right, great. So there's a 4 there. We might still be able to track the ramifications of that down the line. But let's check the rest. So minus 4, okay. That became a minus 5. That became a plus 2, all right. That is good. Let's dot these and then that is good. All right. So since this was the problem, combined with this, when you flip it, you should get a 1 for that. Yeah, and we wrote that as a 3. Okay. All right. Let's put the 1 there and see if we can track the changes again. So this with this is good. This with this is good. This with this is good. this with this. That is good. All right, this with this. Great. All right. That is good. So then this with this is correct. This with this is correct. All right, this is the one that we know is going to be wrong. That should just be a minus right there. And then with this thing, that's going to be a, oh, sorry, with the other one, that's going to be a 2. All right. And might as well check. It's, there could always be another mistake. All right. So let's rewrite this. We should be getting something magical happening because we did confirm that every vector in this third set is in the span of the second set. So we have this. We're gonna write. Okay. And all right. This. Yeah, this is just a lot of bookkeeping right now, so probably not missing much. That's still 4. So let's erase these. This one. One, E2, 5. So that's 7. There's a minus sign. Oh no, that's 4. Okay, great. Plus 4 E2 or E1 wedge E2 wedge E4. And then this final one. Oh well, there's 2 more, but okay, so that and that is going to be a plus 0 E1 wedge E3 wedge E4. And then finally 7 minus 2 minus 3 is plus 2 E2 wedge E3 wedge E4. And this is equal to 16 times 2E1 wedge E2 wedge E3 plus 2E1 wedge E2 wedge E4. Come on, stop lagging, please. Plus E2 wedge E3 wedge E4. All right. So we can basically think of the 3D volume of the parallelotopes of the basis that is set 3 as being 16 times larger than the parallelotopes in the span of basis 2. So that gives us a theorem. Let's prove that theorem. Or this is the whole point of this example was so that I had more motivation for this theorem. If a sub k, which I'm going to say is vector a1 wedge dot 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 all the way up to vector ak, and bk is defined similarly. Bk represent the same subspaces. Wow, it's really lagging. Subspaces which is equivalent to saying that the span of the AIs is equal to the span of the BIs. Then AK is equal to some scalar multiple of BK for M in our field. All right, so we're going to give the proof of this one. And it's not going to, it's essentially the computational proof. It's pretty much just the computational proof. So let me remind you, though, that we determined the formula for V1 wedge all the way up to Vn to be this sum over all permutations, sigma over Sn, where each term is the sign of a particular permutation times the components of the vectors in a certain fashion determined by the permutation. Sigma V2 dot 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 all the way up to Vn sigma n. And we also saw that this definition gave us the same formulas as determinants that we were used to in 2 and 3 dimensions. Okay, so this is the lemma that we need. And here we're thinking of Vi as being equal to Vi1 X1, or sorry, that's not X1, E1. There we go. That's what we want to say. Oh, now it's okay. All right. It's very laggy now. E1, I think that's a call to get a new computer. That would be great. E2 plus Vi, E3 plus dot, 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 all the way up to Vi and En. Okay, so this right here is the key lemma that we need in order to prove that any two representatives of the same subspace are scalar multiples of each other. And in particular, this means that division by these things is well defined, and is what we're going to be needing to get our solid definition of determinant. Right now, we just have this formula for wedging things together, but a determinant has something specifically to do with a matrix. So we want to jump from vectors to matrices, and we'll see how we'll do that. But first, we want to prove this. This is one of the crowning achievements. This is like the first real reason why you'd be like, okay, the wedge product is competitive. So proof. So if span of the AIs is equal to the span of the BIs. How much did you end up missing, Ashrith? Do I need to return? It's like scroll up and cover something that I missed after you showed we're proving. Oh, okay. Well, let me finish writing this down, and then I will just go back up to. Did you see the conclusion of our example? All right, that's one of the best parts. Like it was what all of it was worth doing for to observe this phenomenon. Okay, so when we did the problem I assigned you, we got a minus 2E1 wedge E2 wedge E3 plus 2E1 wedge E2 wedge E4 plus 2 E3 plus E2 wedge E3 wedge E4. And then when we did the one I assigned Matt, we got 16 times that same sum of trivectors, 2 E1 wedge E2 wedge E3 plus 2 E1 wedge E2 wedge E4 plus E1 E2 wedge E3 wedge E4. So in some sense, this one is minus 16 times the other one. And that is what we expected to happen because all of the vectors in the third set are linear combinations of vectors in the second set. So they represent the same subspace. So now we're going to prove this. So we're going to write, if the span of the AIs is equal to the span of the BIs, that means that we can write every BI as a linear combination of the AIs uniquely in one way. So then if we do B1 wedge B2 wedge dot 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 wedge BK, that's going to be equal to BI1A1 plus dot 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 plus we're going to have BIN AN wedge dot 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 wedge. That shouldn't be an I, that should be a 1. These should be ones down here. And this will be BN1 A1. There's a lot of indices being juggled around here. Sorry about that. But this is kind of just taking advantage of like directly of the formula that we have. Like it's literally just by definition, this is going to be equal to the sum. Those should be K's, not N's. All right, these should be K's. K. K. All right. So we have the sum over all sigma in SK times the sorry, this formula is a little bit wrong. On the outside, we had E1 wedge all the way up to dot 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 wedge EN. So basically the unit n vector. And we saw that this was a scalar multiple of it. We saw that this wedge was a scalar multiple of that other wedge. So I mean that's kind of what we proved here anyway, but we're just thinking of it for subspaces now. So this is going to be equal to sine of sigma times B1 sigma 1. Nice. All right, show me your solution at the end. Let's Bn sigma n. That should be K's. All right, and then these should be A's, not E's. A1 wedge dot 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 wedge AK. So this is BK is equal to some scalar, which I guess I'll call 1 over m times AK, which completes the proof. So it means that every area in the plane is a scalar multiple of every other area in the plane. And so that's really nice. What does this have to do with determinants? What how can we move this into understanding what the Pascal matrices are doing in Taylor series? So it turns out it all comes back to just change of basis. So I want to first introduce the idea of a function between vector spaces called a linear transformation. So, let's write this. Call it T of X, but we're thinking of this as a vector that goes from an m-dimensional vector space to an n-dimensional vector space. Okay. Between called a linear transformation. So these turn out to be the nicest possible functions between vector spaces. For the properties, because of the properties that I'm going to say. Wow, this is getting really laggy. So if, I should say, if first, it needs to not do anything to the 0 vector. And second, it needs to distribute over a vector addition. And let's call this vector X. And commute with scalar multiplication. So let me write that out. T of X plus B times T of Y. Okay, so this is a pretty good thing to take a screenshot of. This is what linear transformations basically are. So let's look at some theorems. Linear oh, wow, it is so laggy. Transformations. Ooh, this is getting really bad. Maybe I just have to restart my pad. Preserve. No, it's not helping. I should say linear, and then in parentheses. Come on, please. Independence. That's not quite true. They only preserve linear dependence. Linear dependence. They can violate linear independence, and we'll look at an example of one that violates linear independence later. But they definitely preserve linear dependence. So proof. This is the first theorem. I guess I'll prove the second one afterwards. So, but the proofs are exactly the same. So if we have that VI, I put the I's on top for indices, didn't I? VI is equal to VI1 E1. No. Let's put it this way. B is in the span of AI, where, dang, I am putting these in the top. So it's in the subspace spanned by AI, which means that we can write B is equal to I don't know, x1 a1 plus x2 a2 plus ... all the way up to x, n, a, n. Sure. Well, we said it was between an m to n space. So this is m because we're defining linear transformations from Vm to Vn. All right. So if we take a linear transformation of this, we get t of this. So we can rewrite this as x1 t of a1 plus dot 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 plus xm t of am. And what this implies is that t of b is in the span of t of ai. Does that proof make sense to you guys?
Yeah.
Okay, so what's an example of a linear transformation that does not preserve linear independence? So here's an example. So let's say you go to the grocery store. Your cart is like a vector of groceries. And an example of a linear transformation is the price. I should just say checkout. There you go. Checkout is a linear transformation. So checkout of a grocery, let's say GI, is equal to some, this is specifically a vector, is equal to some price, PI, and this is a scalar, right? So if we had 0 things in our grocery cart, when we arrive at checkout, it's going to cost us $0. So actually, let me just write this as $1. Okay, $0. And if our cart consists of A of grocery 1 plus B of grocery 2, then the price is going to be A times the cost of the first grocery plus B times the cost of the second grocery. So this is an example of a linear independence violating. Because G1 and G2 are completely different vectors. Are completely different. I spelled that wrong. Let's see, complete LE, different. They're linearly independent as groceries, but C of G1 is definitely equal to some constant P times C of G2. So they're not linearly, yeah, slight spelling error, I'm sure. But does this make sense as an example of a linear independence violating linear transformation? It removes linear independence? Okay, great, great. But they do preserve linear dependence, which is going to let us state the second theorem, which the proof is 100% the same as the first. So I'm not going to rewrite the proof. Every linear transformation is completely determined by how it transforms a basis. All right. I'm not going to prove this one because the proof is literally exactly this. It's exactly this. So I am going to state a consequence of this though. Oh, it's starting to cut off things. All right, all right. So consequence. If you pick a basis, that turns a linear transformation into a matrix. A matrix specifically is just telling you how to compute a linear transformation given your uh, given your given a linear transformation and a basis. It tells you how to compute what it does. So for instance, let's return to our grocery example. Let's say we have apples for $2 and or a single apple, I should say, for $2, and a banana is $3. And let's say they'll pay you to take their cucumbers. All right. Very, very accurate grocery store. The matrix representing this linear transformation is 2, 3, minus 1. And your shopping cart is A, B, C. So what do we get if we perform this matrix multiplication? Well, it's just one row times one column. That's 2A plus 3B minus C. Great. So if this is our jumping point into what a determinant is for a matrix. Now that we know that a matrix is a linear transformation, matrices preserve linear dependence. Okay, so we want to keep that in mind. Matrices preserve, come on, preserve linear dependence. And the question that we want to ask is how to take a linear transformation of a wedge product. So how do we understand this? Well, if I take two vectors, right, and I wedge them together, I get something that looks like this. But let's say we're in 3D space, and the linear transformation that I'm going to apply is I'm just going to rotate about the origin, right? That's a linear transformation, it turns out. So what I do is I rotate here to something like that. Here, let me draw a different rotation. Oh boy, it's really struggling now. All right, a different rotation to something that looks like this. Right, so if this was A and B, this is A primed and B primed. It doesn't have to be rotation, but a linear transformation that sends those two vectors to those other two vectors. So wouldn't we want this thing to follow along for the ride? Like if it was a rotation, then we would, if we imagine if the two like skeletal pieces of the bivector are moving, then that whole plane is moving the same way, right? So what I'm really saying is we want, if we just think about it geometrically, that a linear transformation of A wedge B should be the linear transformation of A wedge the linear transformation of B. So this turns out to be the right idea. This is called the outer morphism property. So just I want to touch base here. Can you guys like paraphrase in your own words what this property is saying? There's a couple vocab words that we've used in other parts of the course that you could probably use here that I didn't use specifically to describe it. Property.
Given, is it okay if I dumb it down to my language?
Mm-hmm.
Okay, given two, like, okay, I guess transformations of A and B, so A prime and B prime. The wedge, so yeah, the wedge is just the, like in 2D, it would be area. So the wedge of that area should be the same, assuming it's linear, assuming like the
Yes.
vectors themselves aren't changed, but they're just moved.
Mm-hmm.
They should have the same area.
Yeah. Yeah. And so one way to think about what this lets us do is if we have some sort of just general geometric object, this is explaining some of the applications to computer graphics and computer visions that this technology has. Let's say you have some sort of geometric object that you've rendered. If you wanted to like rotate it on your screen, you could either rotate each piece you could take it apart and rotate each piece individually and then put it back together, or you can just rotate the whole thing all at once. That is what the outer morphism property is saying. But there is actually one more vocabulary word that could describe what we're doing here. And so in order to motivate this vocabulary word, let me prove a small theorem. In one dimension, come on, please, please. In one dimension, the only linear transformations come on, this is lagging a lot. Are scalar multiplication. So what that means is that in one dimension, this becomes a distributive law, like axiom 9, I think, or 8, 7, one of those. So another way of stating the automorphism property outside of the equation is all you need, but to think about it in English or in human terms, wow, this is like really struggling. It is fighting me every single step of the way. automorphism property, that is that linear transformations distribute over wedge. I'm sorry that this sucks so bad. I really don't want to have to make another page. Like I literally charged both of these things for like half an hour before class started. All right. I guess I'm going to start a new one here because we have half an hour left and there's a couple things we need to prove about the determinant, I guess. So let's label this one determinants 511. Okay, so given a linear transformation from the span of the EIs, I guess I might as well put these indices in the top. EI to, again, the span. We're thinking of this as being equal to our vector space, Vn. So these are linearly independent. The linear transformation T, I guess we'll call it, then det of T is defined to be T of E1 wedge dot 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 wedge En. All right, so sorry, det of T times E1 wedge dot 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 wedge En. So can someone tell me what this equation means without talking about coordinates? Like what is this telling us about our linear transformation? Det of T is our stretch factor. Because since EI, this set is a basis for Vn, then T of EI, this set, is a basis for Vn. And then we're going to see, assuming linear independence is preserved, and a determinant of 0 means that this linear transformation violates linear independence, is preserved. Okay, so because so let's see this. Let's see two examples of this in 2D space and 3D space, and then we will see how to prove this, or how, sorry, this is just a definition, but how this lets us prove all of our lemmas about determinants. So example, let's take a general matrix in 2D space of E1 wedge E2. So the way that we can think about what this linear transformation does is it sends E1 and E2 to A comma B and C comma D. And this one was 1 comma 0, 0 comma 1, and we had this square piece right here, and it's being sent to this square piece right here. Okay, so according to our formula, this should be equal to A, B, C, D of E1 wedge A, B, C, D of E2. All right, so let's turn E1 and E2 back into column vectors. So that one was 1, 0. And then we have here A, B, C, D, 0, 1. And so the first one is going to be an A and then a C and then wedge. That's going to be a B and a D, which we can rewrite as AE1 plus CE2 wedge BE1 plus DE2, which is equal to ADE1 wedge E2 plus BCE2 wedge E1. If we flip the sign on the second term, then we can write this as AD minus BC E1 wedge E2. So here we've recognized the determinant of T times E1 wedge E2 is actually equal to T of E1 wedge E2. Does this example help clarify our definition? Great. I'm going to leave the exercise of doing it in 3D up to you. It's basically just doing the determinant computation, and we literally did that last time. It keeps popping up, and this is the reason why. Then our first lemma, or we said that our definition of a determinant of a matrix V1 all the way to Vn, we said that that was equal to this sum, sigma over Sn sine of n, sine of sigma times V sigma 1 of 1, V2 sigma 2, dot, 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 V n sigma n. So let's prove this. So we start with this matrix V1 dot 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 Vn acting on E1 wedge dot 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 wedge En. So that's going to be equal to, all right, so I'm just going to write this as Vi from now on. E1 wedge dot 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 wedge Vi En. But you can check that basically multiplying by E1 to En returns a column of the matrix. So this is actually equal to Vi wedge, V1. So multiplying by E1 gives you the first column. Multiplying by En gives you the nth column. So let me just confirm that that's what we got with our example right here. Multiplying by E1 return to the first column. Multiplying by E2 return to the second column. Yeah, I did remember to record it this time. Yes, so I'll send the recordings. Let's see what we have 20 minutes left. All right, so we get these things, and we actually know from our formula that this is then equal to sigma over Sn sine of sigma. All right, later, Ashrith. V1 sigma 1 dot 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 Vn sigma n times E1 wedge E2 wedge dot 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 wedge En. So then does this proof, I guess, well, this is the same thing. We've kind of done the same things over and over again. We're just refining our definitions of what's happening, and how mixing it with slightly new tools. So the second one, we said that for any element, any permutation that if we applied that to the columns of our matrix and then took the determinant, we would get the sign of that permutation times the determinant of our regular matrix. So that is a consequence of the wedge formula that E tau 1 wedge dot 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 E tau n. There should be a wedge right here is equal to the sine of tau E1 dot 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 wedge En. All right, and then this one was the real nice one. So det of two linear transformations f and g is equal to the determinant of f times the determinant of g. This is the formula that let us define the matrix group of 2 by 2 matrices with non-zero determinant. This was the key formula. And now we can give a proof that doesn't reference the definition whatsoever. Or it doesn't represent reference the coordinates. We don't need the coordinates of our vectors. We don't need to know the inside of our matrix in order to prove that this is true. So I'll let you take a shot at it, Matt, unless you want me just to prove it. And here's my hint. Yes. Det of f times E1 En is equal to f of E1 wedge En. I think this is the best proof of this one, this extremely important fact, because it makes it kind of obvious. Like if you stretch it out once and then stretch it out again, that's the same as if you just did a combined stretch. And so this actually becomes that other vector space axiom that we had, where we said A times BV is equal to ABV. Since n vectors in n-dimensional space are just scalar multiplication, then this is basically just an echo of our vector space axiom at the very bottom.
I'm not coming up with anything.
Okay, so let's start with det of the composition f and g times E1 wedge all the way up to En. Well, that's defined to be fg of E1 wedge dot 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 wedge En. Now let's use the associativity of function composition. So this is f of g of E1 wedge dot dot dot.
Right, that E series determines a vector, or it determines something that can be associative as a verb on.
So this is just a scalar multiple of the original unit n vector, right?
Yeah.
So we have a scalar now, which we can pull out of our linear transformation. So we get det g times det f times E1 wedge E2 wedge dot dot dot, dot wedge En, which is a scalar multiple of this, right? Since E1 wedge all the way up to En is never zero, we can then conclude that det fg is equal to det f det g. No induction required. No coordinates required. If you tried to do it based off of this first lemma, it would suck. And then there was a fourth lemma that we gave, and that was that the det of v1 dot 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 dot, and then at the vith place, we added a vector w, and then vn, that was actually equal to a sum of two different determinants. V1 dot 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 Vi dot 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 Vn in the same spot, plus a determinant where we replaced V1 with W Vn. So this one is just, if we take V1 wedge dot 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 wedge Vi plus W wedge dot 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 wedge Vn, that's just equal to V1 wedge dot 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 wedge Vi wedge dot 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 wedge Vn plus V1 wedge dot 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 wedge W wedge Vn. Oh, more dot dot dots. Lots of implied terms here. Okay, so let's look at some interesting stuff. Okay, so we have 15 minutes left. Let's look at a nice place where calculus is entering this. And then I want to talk about solutions of linear systems of equations, and we still haven't talked about Taylor series and how the Pascal matrices are a change of basis matrix. I'll see what we can do about that. If you and Ashrith are still willing to put up with me, I'll tell you about it because I think it's cool. But I understand if you guys want to enjoy your summer. But let's finish this here. So let's return to 3 dimensions. So our matrix is x1 of t. We have y1 of t, z1 of t, x2 of t, y2 of t, z2 of t, x3 of t, y3 of t, z3 of t. And we take the determinant of this, and then we take the derivative. So what are we saying here? Our matrix, we can think of its columns as sort of the 3 columns are wiggling, 3 wiggling arrows in space. And so they define some sort of unit prism that we're taking as our definition of the unit volume. And so as our function changes through time, how does our unit volume change through time? That's the question that we're asking here. Well, it turns out, since I'm going to call this d dt of the matrix column 1 of t, column 2 of t, column 3 of t. Oh, I forgot to put a determinant symbol here. I'm going to use a notation that I haven't used the whole time, but if you just put absolute value bars around a square matrix, then people are going to, it's going to be implied that that's a determinant. So I'm just going to do that. We can think of this as d dt of column 1 of t, wedge column 2 of t, wedge column 3 of t. So do you know the triple product rule?
I don't, but I imagine it can be solved to a series of 2 doubles.
Yeah. So I'm just going to state it because the symmetry, you can just do 2 doubles. So it's going to be f primed gh plus f g primed h plus f gh primed. And this is actually really related to our Pascal matrices, the triple product rule as well. But it turns out that since we have a product, associative, distributive, we get the product rule for free in this case. So we get C1 primed, very unfortunate notation here, wedge C2, I'm going to stop writing of T, plus C1 wedge C2 primed, wedge C3, plus C1 wedge C2 wedge C3 primed T, which we should have this in E1 wedge E2 wedge E3. These things are constant, so they pass outside of the derivative. I guess I should E1, wedge E2, wedge E3 on the outside here so we can factor everything correctly. And this is actually equal to det the matrix C1 primed, C2, C3 plus det C1, C2 primed, C3 plus det C1, C2 primed, C3 primed. And I know for a fact that no class I've ever been in, not my advanced matrix theory class, not my differential equations class, neither of them have proved that the derivative enjoys a product rule of its columns. Sorry, the determinant enjoys a product rule for the derivative on its columns. None of them have proved that without using induction. But this is just a consequence of the regular triple product rule, or in n dimensions, the n product rule, which looks like this. It's really easy to generalize. So let's talk about really quickly how to solve a system of linear equations with wedges. Solve a system of equations with wedges. And I'm going to state the theorem in n dimensions, and then I am going to prove it. I'm going to show an example in 2 of how to get a proof of it. Yeah, with wedges. And then I've said this a bunch of times, but if you're going to look for a faster algorithm for doing this, that's called row reduction. So if I have this system of equations, a11x1 plus a12x2 plus I should do this the other way around. No, I shouldn't. I am doing it just fine. A12, a13x3 plus ... plus a1 and xn is equal to b1 all the way down to an1 x1 plus ... plus an and xn is equal to bn. So this solution, or this system of equations, has a unique solution exactly when this determinant does not equal 0. A11, a1n to an1 all the way down to ann. And we're going to prove it using Cramer's rule, which I'm going to show you only in 2D, but the argument is exactly the same in n dimensions, and it's very easy to state without using induction. So let's say I have ax plus by, by equals e, a scalar, not a unit vector. Cx plus dy is equal to f. Okay, so first thing I want to do is I want to rewrite this equation like this. A column vector AC times X plus another column vector BD times Y is equal to some column vector EF. So I'm going to call this vector V1, V2, and W here. And so now we have a single vector equation, V1x plus V2y is equal to W. And so you might be thinking to yourself, Corbin, we went from 2 equations and 2 unknowns to 1 equation and 1 unknown. What the hell's going on here? Well, it turns out actually this is really advantageous to us because we can use the wedge product here. If we multiply the equation on the right, or we want to multiply on the right, yeah, by V1, or we want to wedge on the right by V1 equals V1 wedge W. Then we're going to get V1 wedge V2 times Y is equal to V1 wedge VW. Now, a solution exists is the same thing as saying that V1 wedge V2 represents the same subspace as V1 wedge W. So that means that their product or their division is well defined. V1 wedge W time divided by V1 wedge V2, provided V1 wedge V2 does not equal 0. If it does not equal 0, that's equivalent to the determinant being not equal to 0, which is kind of that's where this theorem came from that we're going to prove in 2D using Cramer's rule. So similarly, we can get, if we wedge on the left by V2, that X is equal to W wedge V2 over V1 wedge V2. And so if we look back at our system of equations, we're saying, okay, AX plus BY equals E, CX plus DY is equal to F. So then this is telling us that X is equal to AD minus BC times E1 wedge E2. And then also on top, we're going to have DF minus, DE minus BF. And Y is equal to times E1 wedge E2. Since these are the same subspace, their division is well defined, so I'm not going to write them on the second one. That's going to be AD minus BC on the bottom again. And on top, we're going to have AF minus CE. So you've never seen this before?
I haven't, no.
Huh. Well, this is Cramer's rule. It's kind of the formula for solving a system of linear equations, but in 2D, but don't memorize this formula. You already know that. But I'm gonna state the solutions for 3D and then I'll let you go. So say we have A1x plus B1y plus C1z is equal to D1, and A2x plus B2y plus C2z is equal to D2, and A3x plus B3y plus C3z is equal to D3. We can rewrite this, summarize it as the equation A times x plus B times y plus C times z is equal to a vector D. So then what I'm going to do is I'm going to wedge on the left by B wedge C. And what you get is x times A wedge B wedge C is equal to D wedge B wedge C, which tells us that x is equal to D wedge B wedge C over A wedge B wedge C. Oh, we got to talk about that geometry problem. If you wedge on the left by A and on the right by C, then you get y times A wedge B wedge C is equal to A wedge D wedge C. Oh, now it's starting to lag. So y is equal to A wedge D wedge C over A wedge B wedge C. And then the last one is if you wedge by A wedge B on the left, you end up with Z times A wedge B wedge C is equal to A wedge B wedge D. So Z is equal to A wedge B wedge D over A wedge B wedge C. And there you go. That's Cramer's rule in 3D. And that's a much more compact form than writing with determinants. So let's look at the, any thoughts on this before we move to the geometry problem? What do you think of this in total?
I don't really know what to say other than it's cool how connected they are.
Yeah, that's pretty much like it's really subtle because all these things are so close together, but you can like peel them apart really nicely. It seems like Dr. Shu at UNLV would say it's overkill, it's child abuse. And so in some ways he's right, because in terms of computations, when the systems get big, you want to use row reduction. That's just like the last 150 years of human industry has been applications of row reduction. That's the third proof of the Pascal matrix determinant being 1 is row reduction. Dang, there's so much I wanted to say about how Taylor series is related to this stuff, but we really do not have time because I was at least able to prove all these lemmas, prove another fact about the derivative of determinants, prove Cramer's rule and the connection between the determinant of a matrix and the existence of a unique solution. So much to talk about. Honestly, mathematics is like, or sorry, not mathematics, calculus is like a huge gatekeeper to much more interesting conversations that you can have. But let's see your solution to that geometry problem.